6.9 is integration with substitution. Okay, so if a derivative requires the chain rule, then the antiderivative requires what we call U substitution. Okay, we're going to try it on a function so you can see what it looks like and why it's useful. Okay, so I want to find the indefinite integral. So I'm going to find the integral of the quantity 3x minus 4 to the fifth. Okay, I don't actually know what the integral of the antiderivative of this is anyways. This looks like the chain rule because there's this quantity and it's to the fifth. So it's two things combined. If it was just something to the fifth, I could find the integral. But since it's not, I cannot. So I'm going to do what we're going to call U substitution. So I'm going to take the inner function just like we did with the chain rule, this thing right here. I'm going to let U equal 3x minus 4. Okay, now I can rewrite this as U to the fifth instead of 3x minus 4 to the fifth. But if I bring down this dx, I'm going to have U to the fifth, and I'm going to have dx, and I'm not going to take the derivative of U with U with the x. It's mixing the variables. I need them to have the same variable. So if I'm going to change this to U to the fifth, I want there to be a du with it before I take the integral. So where am I going to get du? I'm going to take the derivative of this. So I'm going to get du equals, I'm going to take the derivative of 3x, which is 3. And then because I'm taking the derivative of the x term, I'm going to write dx. The derivative of negative 4 is 0, so it's going to go away. Okay, now I want to put du here, but I can't just put it there. I have to replace something. Okay, I already changed this u to the fifth. The only thing left in this expression is the dx. So if I can solve this expression for dx, I can make a substitution and then I can do the derivative from there. So I'm going to solve for dx. So dx equals, let me divide by 3 or times by 1/3, 1/3 du. Okay, so for the dx, now I'm going to replace it with the 1/3 du in this expression, so this will be entirely in terms of u. Okay, 1/3 du. I'm going to put the 1/3 in the front, just because that's normally where we put it. I'm going to put the du here. Now this is an expression we can take the antiderivative of because this looks like the power rule. Okay, so let me leave the 1/3 here for now. I'm going to raise u to it. Why am I writing integral? Okay, hold on. 1/3. This is going to be u to the sixth, and I'm going to divide by 6. Let me add a constant. Okay, I'm going to simplify this a little bit. I'm also going to replace the u with the 3x minus 4 so I can rewrite my answer in terms of x because that was what the problem was. So let me make this 1/18. For u, I'm going to resubstitute 3x minus 4 to the sixth, and then I'm going to put plus c. Okay, now let me just double check that the derivative of this is indeed this. So if I bring down the 6, 6/18, this goes down to 3x minus 4 to the fifth, and if I times it by 3 because of the chain rule, I'm going to have 18/18, which is going to cancel out. Derivative of c is nothing, so it worked, and I have it back in terms of x. Okay, let's try it on b, because sometimes things look a little weirder. Okay, for 2, find the integral of 6x squared times x to the third plus 4 to the fifth, the quantity x cubed plus 4 to the fifth. Okay, now there's like multiple things going on here. I have this 6x squared, and I have this quantity to the fifth. I want to try to guess what would make this work by defining u. And I might guess wrong, but I'm just going to try it. And if it doesn't work, I will redefine my u. Now my guess is u is this thing in here. And then I'm guessing that this has something to do with du, because normally when we do the chain rule, at the end we times it by the derivative of the inner function. So this is probably the inner function. So let's try it and then see if it works. So if I do it this way, I'm saying u is going to be x to the third plus 4. Okay, let me take du and then see if that's going to resemble anything in our problem. So this is du equals 3x to the second dx. Derivative of 4 is nothing. Okay, let me look at this now. Okay, so there is a 6x to the second here. There's not a 3x to the second here. But I can make 6x squared, rewrite it as 2 times 3x to the second. So let me rewrite this as 2 times 3x to the second I'm going to keep this as x cubed plus 4 to the 5th for now. And then I'm going to write dx. And I'm going to look at it again. Okay, so I'm going to replace this with u. This is going to be u to the 5th. I see that du is equal to 3x squared dx. I see the 3x squared dx here and here, which means I can replace those two terms with du. Okay, let me bring down everything I have left once I do my u substitution. And you can't do your u's, don't do your u substitution in pieces. You need to do it all at once because you're redefining the integral. Okay, so the 2 is going to stay there. Instead of x cubed plus 4 to the 5th, I'm going to make that u to the 5th. And then the 3x squared dx is going to get changed to du. Okay, now I know how to take the integral of this, so I'm going to go ahead and do that. Okay, so what is this? This is 2 u to the 6th. Why do I keep writing that integral sign? 2 u to the 6th over 6 plus c. Let me simplify it and make my substitution. So I'm going to make 2 6 1/3. For u, I'm going to plug in my x cubed plus 4 to the 6th and bring down my plus c. Okay, and then to check my answers, I can always take the derivative of this and make sure it equals to this. If I bring down the 6, that's 2. X cubed plus 4 to the 5th, and then if I do chain rule, I times it by 3x squared, and the 2 times the 3x squared gives me the 6x squared. Okay, let's look at some other ones, because this is tricky. Okay, here's C. Okay, C is the integral of the quantity root x minus 1 squared over root x. Okay, again, there's two things kind of going on. There's this thing up here, and then there's this thing down here. One of them is going to be my u. One is going to have to do with my du. Okay, since I see some quantity being squared, I'm going to assume that that's my u and try it. Okay, let me think about the du. The du could have to do with this. Let's take du and see if it looks like that. What is that? 1/2 x to the negative 1/2, so 1 over 2 root x. Derivative of negative 1 is nothing. Let me write my dx. Okay, now I'm going to look back at my original expression and see if we can't make a substitution. Okay, so I can see this is going to be u squared. That's okay. Let's see, what do I have over here? I have 1 over 2x dx. So I see the root x and I see the dx. I don't see the 2 there. So I don't want the 2 to be there. So let me change this by canceling the 2 over to the other side. So I'm going to times 2 to the other side so that it looks more like my original equation, 2 du. Okay, now let's see. Now I have 1 over root x, the dx, over root x dx, and I can replace that with 2 du. Okay, let's plug that in and then see what that looks like. Okay, now let me see. The 2 du, I'm going to put the 2 in the front. This is the 2 coming from right here. Let's make that root x minus 1 is u squared. I'm putting the du at the end just because that's customarily where we write it. Okay, and then I'm going to look at it and make sure I can take the antiderivative now. Antiderivative is 2u cubed over 3 plus c. Okay, let me substitute back in my original expression for u. Okay, and then that should be my answer. You can always take the derivative in your head to double check. Okay, let's look at D. Okay, I have sine of x times e to the cosine x. I have to do a substitution. I have sine x here, and then I have e to the cosine x. So it might be the cosine x, it might be the sine x. It's probably the cosine x. Just because I'm thinking in my head, if I did e to the cosine x and I took the derivative of cosine has to do with sine. So that's probably where it came from. Now, if I guess wrong, I'm going to find out because I'm not going to be able to take the derivative. I'm not going to be able to do the antiderivative. Okay. du. Negative sine x dx. Okay, now let me look back at my original equation. I'm going to make this e to the u. Once I do that, I'm going to be left with sine x dx, which is really close because I have sine x dx, but I don't have the negative sign. So let me give the negative to the du. Okay, now I have sine x dx, and I can replace that with negative du. So over here, I'm going to put a negative and a du. Negative e to the u du. Okay. Let's see, the antiderivative of e to the u is just e to the u. So this is going to be negative e to the u plus c. Okay, substitute back in my u. Okay, and then that's going to be my answer. Again, you can always check in your head. Negative e to this something is going to be negative e to this something. The derivative of cosine is negative sine, and so the negative times the negative sign made this a positive sign. So it looks like it works. Okay, let's look at f. Hopefully you're getting the hang of it. So of course it's going to get harder. Okay, we have cotangent of 3x. So it seems like u is going to be 3x. Okay, so du is 3dx. Okay, what's left here? I have dx. I don't have the 3. So let me solve for dx. I'm going to make this, I'm going to divide by 3 or times 1/3. So 1/3 du is dx. Okay, so now I can change dx to this thing. Here. Okay, now 1/3, I might as well just put the 1/3 on the outside and not think about it for the moment. The cotangent of u du. Okay, now this looks like a nice problem, except for what is the antiderivative of cotangent? I have no idea. Okay, since I don't know the antiderivative of cotangent, we're going to have to try again. I'm not going to start over again, but let's think of what I can do with cotangent. Okay, let me at least try to rewrite this. Cotangent is cosine u over sine u. Did that make it better? I mean, not necessarily. I still don't know the antiderivative of this, but I could do u substitution again and then see if we can't kind of figure it out from there. Okay, so I have two things. I have a cosine u and a sine u. Which one do I want to do u substitution with? Okay, now if I'm guessing, when I do chain rule, I normally have some kind of function and then I take the derivative and then I times it by the derivative of that inner function. Since I'm timesing by the inner function's derivative, I'm thinking cosine u has to do with du, which means sine u is probably having to do with my function. Not sure. We're going to try it. If it doesn't work, you will know because it's going to fail. Now, I can't let u equal this again because I already used u. So let's try v. Let's try w because my v's sometimes look like u's. Okay, let's try to make w equal sine u. Okay, then dw equals the cosine of u du. Now let me look again. Okay, I substituted for sine. The cosine u and du are left, which is exactly what I have here. So this actually worked. Okay, now let me make my my w substitution. Okay, so w is sine u, so this is going to be 1 over w. And then the cosine u du will be dw. Can we take the antiderivative of this? Yes. The antiderivative of 1 over w has to do with ln. So this is going to be ln of w plus c. Okay, now I need to go back and resubstitute in all the stuff I substituted for because I can't leave it like that. I was in terms of x. Okay, so let's go back now, start resubstituting. For w, that was sine u, so this is the absolute value of sine u plus c. Okay, but I can't leave a u in there because I'm trying to do this with the integral with respect to x, so 1/3 ln for sine, for u, I let u equal 3x. Okay, now I'm going to do plus c. Okay, now this should be our final answer because I'm back in terms of x. I can absolutely recheck this in my head. Let's look. Derivative of ln is 1 over x, so 1 over sine of 3x. The derivative of sine is cosine, so I had cosine over sine, which is how I got the weird cotangent, and then I times it by the derivative of 3x, which was 3. 3 over 3 was 1, which is why there's no 1 there. You don't have to check it every time, but if you're not confident, you should double check. Okay, let's keep going. Okay, let's look at g. Okay, it's the integral of x over the quantity square root of x plus 1 over dx. Okay, since I'm square rooting the x plus 1, let's let u equal the x plus 1. Okay, let me take the derivative. Du equals derivative of x is 1 dx. Okay, did that help me? Okay, so I got dx, and I can replace that with du. So far I have 1 over the square root of u, but what the heck am I going to do about this x situation? I mean, now I know that u equals x plus 1, so I could solve for x here. Let's see. X equals u minus 1. Would that help me? So then I'll have u minus 1 in the numerator, the square root of u du. Let's try it and see if it gets anywhere. Okay, it still looks kind of bad, doesn't it? Can we fix it? We can fix this. Since the denominator is a monomial, well, it's not a monomial, but it's a single term. We can divide this by this and this by this and use the power rule. So let's rewrite this. Okay, u over the square root of u is u to the 1 over u to the 1/2. So 1 minus 1/2 is u to the 1/2 minus 1 over square root of u is 1 over u to the 1/2, which is u to the negative 1/2. Okay, and I can take the antiderivative of this. I'm just trying to get to something I can do something with. Okay, let me do this. Okay, let me raise it a degree. So it's to the 3/2, and I'm going to divide by 3/2, which is timesing by 2/3. Okay, next one. Let's raise it to a degree, so now it's 1/2. I'm going to divide it by 1/2, which is like timesing it by 2, plus c. Okay, this is my final answer. If I want to take the derivative of this, I should end up getting that. Okay, let's look at h. H is kind of a special case, but let's imagine if we've been doing it the way we've been doing it, 1 over the square root of 1 minus 4x squared, I would think like maybe u is 1 minus 4x squared. Okay, if u is 1 minus 4x squared, then I'm going to take the derivative of u, and I'm going to get negative 8x dx. There's no extra x terms up here. So there must be something else going wrong. So when I stare at this, I also look at it and it kind of looks like the derivative of arc sine. If this was the derivative of arc sine, this would be 1 minus something squared. So what do I square to get 4x squared? 2x. Okay, so let me look at this. If I were to let u equals 2x, let me rewrite this. No, actually, let me take the derivative first. So du equals 2 dx. If I put a u here, this would be 1 minus u squared. I'm okay with that. The derivative of u is 2 dx. No, I don't have a 2. All I have is a dx. Okay, so let me move that 2 to the other side. Divide by 2. So 1/2 du equals dx. So now I can replace the dx with the 1/2 du. Okay, let's do that and then see why this is going to work out. Okay, the 1/2 is a constant. I think I'm just going to move it to the outside. 1 over 1 minus u squared du. Okay, so for dx, I plugged in 1/2 du. I put the du here. Since the 1/2 was a constant, I just moved it to the front. Okay, now when I look at this, I should know what the antiderivative is. Okay, this is the derivative of inverse sine, so this is the antiderivative is arc sine of u, or inverse sine of u, plus c. Okay, so this is going to be my final answer. You could also say inverse sine. These are kind of tricky, though. You kind of have to think, does it kind of look like a derivative of an inverse trig? And then it normally means that you couldn't do chain rule because the derivative of this inner function isn't somewhere present, which makes it more confirming that it's some kind of inverse trig. Okay, now let's look at some definite integrals. Okay, we're going to go ahead and do definite integrals. Remember, definite integrals have a lower and an upper limit, so I'm going to evaluate it and actually get a numeric answer, most likely. I can still use u substitution. The only thing is, when you substitute for whatever variables included and you change the variables, you're going to end up changing the bounds depending on the variables. So that's what we're going to be really careful of. That'll be the new part. Okay, let's try this one. We're not going to worry about that at the moment. We're just going to try to take the integral. Okay, so I have the integral of t squared times the square root of t cubed plus 1. So I'm thinking u is this. And I can tell that the derivative of this is something to do with t squared. Derivative of 1 is 0. Okay, because I have a t squared and a dt, I'm going to try to isolate the t squared and the dt, so I'm going to move the 3 to the other side. Okay, I'm going to make the u substitution and then I'm going to reconsider my boundaries because my boundaries are going to be messed up in a second. Oh, there's a 1/3. Let me put the 1/3 on the outside. Okay, so I have the square root of u du. Okay, now the initial boundaries were from 0 to 2, but they were representing the initial boundaries of t, like the initial values of t. I've changed it to u, so I need the starting and ending points for u. Okay, so the lower limit was when t equals 0. So now I want to see what happens. What is the lower limit for u? Well, the lower limit for u is when t equals 0. So let me see when t equals 0, what u equals to. I'm going to write u of 0. So that's 0 cubed plus 1. So the lower boundary is going to be 1. Okay, the upper boundary of t was 2. So what's the upper boundary of u? Well, that's going to be 2 cubed plus 1, which is 9. So I'm changing the boundary of the integral because I changed the variable. So it's the same integral, but because I changed the function, I have to change the boundaries. But they are equivalent. They were not equivalent before. Okay, now let's evaluate it. Okay, 1/3 antiderivative of the square root of u. So that was u to the 1/2, which is going to make it u to the 3/2 divided by 3/2, which is timesing by 2/3. I'm not going to bother with the constant because I'm going to evaluate this from 9 to 1, 1 to 9, I should say. Okay, I'm going to simplify the coefficient. So this is 2/9. Okay, let me do 2/3. No, I took out 2/3. 9 to the 3/2 minus 1 to the 3/2. Okay, 9 to the 3/2. The 9 to the 1/2 is the square root of 9. So I'm square rooting the 9, which is 3. 3 to the 3rd is 27. 1 to the 3/2 is 1. So this is 26 times 2 is 52 over 9. And since this is a definite integral, this is the answer. I don't have to worry about switching it back to the certain variables because I changed the numbers I plugged in so that the result will still respect the initial boundaries. Okay, let's try one more. Okay, the integral from 0 to pi over 2 of cosine x times the square root of sine x dx, u. Sine x, because I'm square rooting the sine x, the derivative of sine is cosine, so it seems like u should be that inner function. Du, cosine x dx. Okay, let's see what substitution we can make here. Okay, so what else do I have? I have the cosine x in the dx, cosine x dx, so I can straight substitute du. So this is going to be written as square root of u du. Okay, but since this is a definite integral, I need to change my boundaries. So the lower one, 0. X is 0. So let me plug in x is 0. The sign of 0 is 0. Upper limit, pi over 2. So when x is pi over 2, u is the sine of pi over 2, which is 1. Okay, let's take the antiderivative and then we will evaluate it. This is u to the 1/2. Now this is u to the 3/2 divided by 3/2, which is timesing by 2/3. And I'm going from 0 to 1. Which is 2/3 times 1 minus 0, so just 2/3.